Yes, hello friends. Welcome to the session. Continuation of chapter 7. I am discussing about DC bridges. In the last sessions, with respect to DC bridges, I discussed about measurement of medium resistance and measurement of high resistance. Then the last concept with respect to DC bridges is measurement of low resistance. Okay, I already told that in the introduction I given low resistance is the difficulty in the measurement of low resistance is one difficulty is because of lead wire or connecting wire resistance or contact wire resistance, the errors are more. That means in the measurement of low resistance, if any lead wire resistance or connecting wire resistance, okay, generally this is the resistance representation, but we can represent this low resistance with 4 terminals. These terminals are voltage terminals and these terminals are current terminals. Yes, why you are representing with 4 terminals is to make the resistance is definite value and precise value. That's why it is represented with 4 terminals. What do you mean by definite value or precise value? Means definite, to make the resistance is definite and precise value, then it is represented with 4 terminals. For example, we are measuring 0.1 ohm resistance. If it is represented with 2 terminals only, what is the problem? We are measuring with 0.1 ohm resistance. The example of low resistance I told already. If the resistance is less than or equal to 1 ohm, then that resistance is treated as a low resistance. We are measuring 0.1 ohm resistance. Let this connecting wires is having the resistance of 0.02 ohms. Let us assume that. If this 0.02 ohms is added with 0.1 ohm, then it gives a very serious error. That's the reason why we can make the resistance is definite value or definite and precise value. Then it is represented with how many terminals? 4 terminals. Yes, low resistance is represented with 4 terminals. Now, the another difficulty in the measurement of low resistance is if there is some error is introduced due to thermoelectric EMFs also. There is some error is introduced due to thermoelectric EMFs also. That's why during the measurement of low resistance, that effects also we can eliminate. Then we can eliminate the effect of lead wire and connecting wire resistance. Then only we can measure the low resistance is more accurate value. Then to measure the low resistance is more accurately, what are the methods we are using? One method is the Kelvin double bridge method. These are the different methods used to measure the low resistance. Kelvin double bridge method. Kelvin double bridge. This is one method we are using for measurement of low resistance, and AV method, that is ammeter voltmeter method. Ammeter voltmeter method. The third one is potentiometer method, pot method, for measurement of low resistance. Okay, but I already discussed the AV method in the measurement of medium resistance. That is a special case. We are using AV method for measurement of low resistance also. Potentiometer. These two in this session I want to discuss these 2 methods. Kelvin double. But in detail about potentiometer in the measurement of voltages I already discussed. Okay. Now, but here I am explaining this potentiometer for measurement of low resistance. Okay. These 2 methods I want to discuss. So many other meters also there for measurement of low resistance. We can use microampere ohm meters. Okay. Then by using that meters also we can measure the low resistance. But particularly the more preferable method and more accurate method is more accurate to measure the low resistance. More accurate and more preferable method to measure the low resistance. Okay. Now first I want to discuss Kelvin double bridge. At the end I will discuss the potentiometer method. Okay. Now concentrate. Once again I am telling that the difficulty in the measurement of low resistance is connecting wire resistance or lead wire resistance. That is one difficulty. It gives a serious error. Even thermoelectric EMFs also causes the errors in low resistance measurements. Okay, that 2 points you remember. Concentrate on Kelvin double bridge. Measurement of low resistance by using Kelvin double bridge. No doubt at all. This Kelvin double bridge is a modification of Wheatstone bridge only. It is a modification of Wheatstone bridge. But why the name is given as a double? The name is given as a Kelvin double bridge means mainly Wheatstone bridge consists of only one ratio arms. P and Q is the one ratio arms it consists. But it consists of two sets of ratio arms. Capital P, capital Q and small small q. Why you are using additional set of ratio arms means by proper selecting the ratio of that is called inner ratio arms. By selecting the ratio of inner ratio arms, then we can eliminate the effect of lead wire or connecting wire resistance. Then we can measure the resistance more accurately. That's why you are using the additional set of ratio arms. Because it consists of two ratio arms, that's why name is given as a double bridge. No doubt at all, it is a modification of Wheatstone bridge only. First you draw this bridge, then we will see what is the expression for unknown resistance by using this Kelvin double bridge. Okay. All of you draw this one. Sorry. This galvanometer, parallelly note down, don't wait. The small r is lead wire or connecting wire resistance that connects the unknown resistance or standard known variable resistance capital X. Okay. In the case of Kelvin double bridge, we can use reversible switch. The purpose of reversible switch I will explain. This battery EMF is E. Okay. Let this node is A, B, C, D. This position is M and this position is N. Okay. Now this is the small r is the lead wire or connecting wire resistance. This capital P and capital Q, and this is small p and small q. Okay. Where capital P, capital Q is outer ratio arms. Outer ratio arm resistances. Here small p and small q is inner ratio arms. Inner ratio arms. Okay. Then what is the small r? Lead wire or connecting wire resistance. Connecting wire resistance. Yes. Where R is the unknown resistance. Where small r is also called, it is a link connected between unknown resistance and standard resistance. It is a link connected between unknown resistance and standard. That terminology also we can use. It is a link connected between unknown resistance and standard resistance. R is unknown resistance. Where S is standard known variable resistance. S is a standard known variable resistance. Okay. Now we want to measure the unknown resistance. Let us assume that bridge is under balance condition. If the bridge is under balance condition, the current through the galvanometer is 0. Now you want to apply the balance condition. What is the balance? Product of opposite resistances are equal. But that condition is applicable if the bridge consists of 4 arms. But here the number of arms are more. Now you want to convert this bridge into 4 arms. Then we can apply the balance condition. Now in order to convert this bridge into 4 arms, then you can convert this delta to star connection. Okay, this switch is nothing but a reversible switch. The purpose of reversible switch I will explain. Okay, this is the reversible switch arrangement. Reversible switch arrangement. Okay, now we want to make this bridge as a 4 arms. Convert this delta to star. Convert this delta to star. Then opposite to N, you take Rn. This resistance is Rn. Okay. Opposite to M, you take this resistance is Rm. Opposite to D, take this resistance is Rd. Now, we are converting delta to star. How to make delta to star conversion? This you already know. We are converting this delta to star. Now, for example, I want Rd. What is value of Rd equal to? Okay, what is Rd? You tell me. This Rd means opposite, small p into small q, delta to star conversion, that you know, by total resistance, p plus q plus r. Can you find what is Rm? Tell me what is Rm value. This I want. Opposite resistance, small p into small r. Small p into small r by p plus q plus r. Yes. Now I want, this is Rn, this resistance Rn, opposite resistance. What is Rn? You tell me. Rn equal to QR by S, P plus Q plus R. Like this we are converting this delta to star. After converting this delta into star, then remove these resistances. Now this consists of 4 arms. Then what is that arms? And this is one arm. This total is one arm. And this is the another arm. Okay. And this is one, and this is one, this is one arm, and this is one arm. 4 arms. But what is this arm? At balance condition, then what is the current through galvanometer? The current through the galvanometer is 0 at balance condition. Okay. Then there is no effect of this arm. That is a galvanometer arm. Then at balance condition, the current to the galvanometer is 0. Then apply the product of opposite resistance. Apply the product of opposite resistance at balance condition. Now, can you apply the product of opposite resistance at balance condition? What you can get? Tell me. This I am doing to measure the unknown resistance at balance condition. Okay. Then at balance, the current through the galvanometer is 0. Okay. Then product of opposite resistance means P into these two are series, S plus Rn. That is capital P into S plus Rn is equal to this one, Q into opposite resistance. This one, Q into R plus Rm. S R plus Rm. Then from this, what is R plus Rm? You tell me. R plus Rm equal to capital P by Q into S plus Rn. Now you substitute Rm and Rn values. Then R plus, what is the Rm? This Rm equal to PR by P plus Q plus R. PR by this P plus Q plus R is equal to P by Q into S. P by Q into S plus what is Rn? This Rn equal to QR by P plus Q plus R. Yes, QR by P plus Q plus R. Shall you write like this? R equal to P by Q into S plus P by Q into QR by P plus Q plus R minus this, bring this side, this minus PR by P plus Q plus R. Then what is unknown resistance? R equal to P by Q into S plus QR by P plus Q plus R is common. Then what we can get? Capital P by capital Q. Here I am bringing QR is common, but QR is not present. PQ is present. If Q is common means by Q you can get small p by small q. Okay, this is the measurement of unknown resistance by using Kelvin double bridge. This formula directly remember. Therefore, what is the unknown resistance? R equal to P by Q into S plus QR by P plus Q plus R, capital P by capital Q minus small p by small q. Like this we can measure the unknown resistance by using Kelvin double bridge at balance condition. But one observation here, this resistance includes lead wire resistance or connecting wire resistance also. Then whatever the resistance measured by using this formula, it is not a true value. When we can get the true value, we can eliminate this smaller effect. Then only we can get the exact value of low resistance. Okay, now how to eliminate this effect? Yes, one observation here, if we select the inner ratio arms, small p and small q is the inner ratio arm resistance. We can select this inner ratio arms in such a way that the ratio of inner ratio arms is equal to ratio of outer ratio arms. If these two are equal, then this value becomes 0. Once this value becomes 0, this total will become 0. Once this total will become 0, if there is any small r is added to this value, no, then we can measure the accurate value of low resistance. That means in this, how to eliminate the effect of lead wire or connecting wire resistance. Therefore, if capital P by capital Q equal to small p by small q, if capital P by capital Q equal to small p by small q, then unknown resistance R equal to P by Q into S. Therefore, effect of connecting lead wire resistance is eliminated. Lead wire resistance is eliminated. Resistance is eliminated. And unknown resistance is measured more accurately. Resistance is measured more accurately. Okay, this is the purpose of using inner ratio arms. If these inner ratio arms are not present, is it possible to eliminate this effect of lead wire or connecting wire resistance? No. Then whatever the resistance measured is not accurate value. Okay, like this we can measure the unknown resistance more accurately by using Kelvin double bridge. For example, if it is selected in such a way that if capital P by capital Q is greater than small p by small q, if capital P by capital Q is greater than small p by small q, this difference gives positive value na. Once this difference gives positive value, this is added to this total value. If it is added to this value means then we can get the high resistance. That gives the greater than the true value. That means if you select capital P by capital Q is greater than small p by small q, then whatever the resistance is measured, that resistance is greater than the true value. Clear? Now, if we select like this, if capital P by capital Q is less than small p by small q, that means these ratio arms we are selecting, this is less value and this is high value, then this difference gives negative value. This difference gives negative value means this total value is subtracted from this one. Subtracted from this one means this value gives the low value. That in that case, the Kelvin double bridge measures the R measured is less than the true value. If capital P by capital Q equal to small p by small q, then what is the resistance measured? If capital P by capital Q equal to small p by small q, then what is the resistance measured? R equal to R3. That value equal to true value of resistance. Okay, that means by selecting the inner ratio arms in such a way that then we can measure the true value of resistance. Clear? Okay, this how we are measuring the unknown resistance more accurately by using Kelvin double bridge. One observation here, what is the purpose of using reversible switch in the case of Kelvin double bridge? What is the purpose of using a reversible switch in the case of Kelvin double bridge? Yes, you tell me. Yes, I told one not only effect of lead wire or connecting wire resistance, there is effect of thermal electric EMFs also. Because of thermal electric EMFs also, whatever the low value of resistance we are measuring, that will not give the accurate value. Now to eliminate that effect of thermoelectric EMFs, we are using reversible switch. Now using reversible switch, we can take the two sets of reading. Instead of taking one reading, we can take the two sets of reading. Once we can take the two sets of readings, then average, by taking the average of that set of readings, we can eliminate the effect of thermal EMF. Now for example, let us assume that this is 2 2 dash and this is 1 1 dash. First connect, 1 is connected to 2, 2 dash is connected to 1 dash. Then we can measure the unknown resistance R. Now we can reverse the switch position. 2 dash is connected to 1 and 2 is connected to 1 dash. Again we can measure the resistance, unknown resistance. Then take average value of those two readings. Then we can eliminate the effect of thermal EMF. Because thermal EMF is directional sensitive. Understood? If you change the switch, you can change the switch positions, then EMF direction is also changes. That average of that EMF will be eliminated. Clear? That's why very important point. Note, in Kelvin double bridge, a reversible switch is used. A reversible switch is used. A reversible switch is used to eliminate effect of thermal EMF. Effect of thermal EMF. Thermoelectric EMF. That is the purpose of using the reversible switch. Okay. Then by taking the set of readings, how this effect of thermal EMF is eliminated? It is eliminated. It is eliminated by taking set of readings and taking the average value and taking the average of readings. Okay, like this we can eliminate the effect of thermal EMF and taking the average of readings. Then whatever the error is there due to thermoelectric EMFs, that is eliminated by using reversible switch. Okay, this about in detail what exactly Kelvin double bridge. Okay, for computative point of view, directly you remember this formula. We can expect the question based on this formula directly. And these points also you remember to answer any theory questions. Okay. Now, for example, if this bridge is under unbalanced condition, then how to calculate the current through the galvanometer? Then how to calculate what is the voltage induced across the galvanometer? Now, one or two formulas I want to explain here. Write down. Kelvin double bridge under unbalanced condition or unbalanced Kelvin double bridge. These conditions, all these I given at balanced condition only. Concentrate, unbalanced Kelvin double bridge. Unbalanced Kelvin double bridge. Yes. If the bridge is under unbalanced condition, there is a current through galvanometer and there is a voltage is induced across the galvanometer. We know that This is M and this point is D and this point is N and this resistance smaller, that you know all this before this one what actual bridge. Okay, now there is under unbalanced condition, let assume that there is a voltage induced across the galvanometer. Then I want to find what is the voltage induced across the galvanometer. Let E naught is the voltage induced, or you take small e. E is the voltage across under unbalanced condition. At unbalance, let small e is the voltage induced across the galvanometer. Small e equal to, now I want this voltage. This voltage is nothing but I want voltage difference between B and D. Voltage difference between D and means this voltage and this voltage. This voltage minus this voltage. That is EAB equal to EAMD. Yes, EAB minus EAMD. Is correct? I want voltage difference of this one. That is the voltage induced across the galvanometer. Now voltage difference means you calculate this voltage and this voltage. This voltage is nothing but EAMD. Understood? Now shall you write like this? What is EAB equal to? EAB equal to. Then what is EAB means? Now I want this voltage. That is voltage across the resistance P. Okay. Now let the total voltage equal to this voltage. The total voltage is how much? E. The total voltage is E. Then shall you write like this? A to B. This A, this is B, this C, this is C. The total voltage is nothing but E. That voltage is nothing but EAC. Na? Shall you write like this? EAB equal to voltage divider rule. Total voltage into that resistance. What is the total voltage? EAC into P by EAC into P by. Then these two resistances are series, P plus Q. Or shall you write like this? P into total voltage is how much? EAC by P plus Q. This is the measured EAB. EAC is nothing but total voltage, A to C. This is equal to, these two parallel now. This is equal to EAC. Now I want EAMD. How to calculate EAMD? Tell me. This voltage you want, EAMD voltage. This voltage you want. What is this resistance? You know. Then what is this resistance? You know. Okay. Now what is the total voltage? Total voltage equal to EAC. Total voltage equal to EAC. Understood? EAC is nothing but E. Now what is EAMD? What is this resistance? R plus. What is this RM? That is R plus RM into R plus RM. I want voltage across this resistor. Voltage across this resistor means R plus RM into what is the total voltage? EAC by total resistance. Then what is the resistance connected for this arm? This resistance is connected and this resistance is connected and this resistance is also connected and this resistance is also connected. Clear? Then what you write? R plus S plus RM plus RN. Correct? Then shall you write like this? EAMD equal to R plus what is RM? RM is how much you calculated now? Yes, RM. RM is nothing but this opposite resistance, PR by P plus Q plus R. This already given RM. PR by P plus Q plus R into EAC by R plus S plus what is RM? PR by P plus Q plus R. What is RN? RN is nothing but a QR by P plus Q plus R. QR by P plus Q plus R. Like this we can measure the EAMD. This is EAMD and this is EAB. This difference gives the voltage across the galvanometer. Clear? Once you know the voltage across the galvanometer, then I want to, let us assume that this is the Thevenin's voltage. Okay. Now I want to find Thevenin's resistance. Then how to calculate Thevenin's resistance means, now how to calculate RTH. Then to calculate RTH, now see this capital P and capital Q is in parallel. This is capital P and this is capital Q. And this is which resistance? Galvanometer resistance. Let this is Rg is the galvanometer resistance. Next, small p and there is ratio arm resistances also. Before that, R and S is also parallel. This R and S is also parallel. Okay. Then small p and small q is also parallel. Small p and small q is also parallel. Okay. These resistances you want. But this Rg is negligible. Rg is negligible. And capital R and capital S is also small values. Okay. This is also negligible. Then if it is negligible, then what you can get? Equivalent. Then capital P and capital Q. And this is small p and small q. Okay. Then what the RTH you tell me? Then the RTH equal to, these two are in parallel. These two are in parallel. Shall you write like this? PQ by P plus Q plus small p small q by small p plus small q. Like this we can measure the RTH. This is a measurement of RTH. Yes, these two are parallel means PQ by P plus Q. This is small p small q by small p. Then these two are in series. That resultant RTH I am giving. Clear? Now, actually we are calculating the current through galvanometer means here we are calculating. Here we are measuring the RTH. Across this we are measuring the RTH. Here we are measuring RTH means galvanometers. Neglect this R and S is negligible because it's very small values. And this is in parallel. This parallel and this parallel, this total combination is series. Okay, no need to connect this Rg value because we are applying Thevenin's theorem across Rg. Clear? Now, once you know the RTH and what is the voltage across the galvanometer, then you find what is the current through galvanometer. Then according to Thevenin's equivalent circuit, this Thevenin's voltage is E calculated. Then we are applying the Thevenin's resistance, this RTH you know. Then we are finding the current through galvanometer. Let us assume that galvanometer resistance is Rg. Then this current equal to Ig. Then what is the current through galvanometer? Ig equal to E by RTH plus Rg. Like this we can calculate. If any unbalanced case is given for Kelvin double bridge, you concentrate on how to calculate E equal to EAB minus EAMD. How to measure EAB, how to measure EAMD. Then difference of that gives E. Then RTH how to calculate. You consider capital P and capital Q and small p and small q. But this R and S is negligible because it's very low values of resistances. Understood? Because we are measuring unknown resistance is very low value. For balance of bridge also whatever the S we are using very low value. That is also negligible. That's why I am taking this capital P and capital Q and small p and small q only. Clear? Then we can measure what is the voltage across the galvanometer and current through the galvanometer. Okay, this is in detail about measurement of resistance by using Kelvin double bridge. Then what is the analysis of Kelvin double bridge under unbalanced condition? Okay, these formulas you know them. Quick. Okay, with this Kelvin double bridge is completed. Over? Yes. The next method for measurement of low resistance is you concentrate on potentiometer method. Part. This simple method for measurement. In detail about potentiometer, how to measure the voltage, I already discussed in the previous chapters. But here, a small formula I want to write how to measure the resistance by using potentiometer. Potentiometer method. Yes. For this small circuit, you see how to measure the unknown resistance by using potentiometer. That this is the battery. We know that low resistance is represented with 4 terminals. Let this current is working current, IW. This is battery. Okay. Now, this arrangement we can use. This is 2 potentiometer. 2 part. Here I am not drawing the total potentiometer circuit. Okay. Let this is S is the standard known resistance, X is the unknown resistance. Let this is 1 dash and this is 2 dash. Okay. Now, where S is the standard known variable resistance, standard known variable resistance, known variable resistance. X is unknown resistance or standard known resistance only, not a variable, standard known resistance. X is unknown resistance. Yes. First keep the switch at 1 dash position. Keep the 2 steps experiment. Keep the switch at 1 dash position and measure the Vs voltage across standard resistance using potentiometer. That potentiometer total setup I am not giving, That setup I already given in the previous chapters. Okay. But sir, why particularly we are using potentiometer to measure the voltage? I told now, potentiometer is works on the principle of null deflection or zero deflection principle. That's why potentiometer is the more accurate instrument to measure the low voltages. Understood? Here measuring very low resistance, current is also very small, the measured voltage is also very small. That's why to measure the low voltages more accurately, we can use potentiometer. If the measured voltage is whatever the voltage we are measuring, that voltage are more accurate, then resistance measured is also more accurate. That's the reason why we are using potentiometer. Clear? Now measure the Vs using potentiometer. Now keep the switch at x to 2 dash position, and measure Vx using potentiometer. Two steps of experiment. But throughout experiment, this IW is maintained as a constant. If the switch at 1 dash position, this working current is constant. If the switch at 2 dash position also, the working current you maintained as a constant. Now, what this Vs gives, you tell me. Then we know that Vs equal to IW into S. Vx equal to IW into X. Clear? But this Vs and Vx values known from the potentiometer. Now, shall you write like this? Vs by Vx equal to IW into S by IW into X. Okay. Now, from this S by X equal to Vs by Vx. But I want X value. The unknown resistance X equal to Vx by Vs into S. Okay. This is the measurement of unknown resistance by using unknown value of low resistance by using potentiometer. Yes, this Vx value is measured from potentiometer. Vs is also measured from potentiometer. It is a standard known resistance. This is more accurately measured. This is also more accurately measured. That's why X is also more accurately measured. Like this, we can measure the unknown resistance by using potentiometer. Clear? Concentrate. Quick. Okay, like this, we can measure the different values of resistance using different methods. In this chapter 7, DC bridges, I discussed about what are the methods used for measurement of low resistance. What are the methods used for measurement of high resistance? What are the methods used for measurement of medium resistance? All these I discussed in detail. For any competitive point of view, whatever the theory concept, whatever the formulas, whatever the analysis I given, that points you concentrate, then you can answer any question. Okay. Now, in this chapter 7 in DC bridges, before starting the AC bridges, I want to solve some classroom workbook questions. After completing this classroom workbook questions, then in chapter 7, I will start the AC bridges. Okay. Now, before going to the next session, you concentrate this note. With this, except classroom workbook, the DC bridges concepts are completed. Okay, you write as some points, some important points I am writing here. Earth resistance is measured by earth resistance. Yes, earth resistance is measured by. How to measure the earth resistance? One is fall of potential method. This one method we can use. Some important points I am writing. This in order. And another one is earth tester. Fall of potential method and earth tester. Then point to remember, earth tester is a special Earth tester is a megger. It is one of the megger circuit with additional features of. It is also one of the megger circuit. Earth tester is a megger with additional features of one is rectifier. Internally it consists of one rectifier arrangement, rotating current reverser. Okay, this is the one of the special megger circuit. Earth tester is one of the special megger circuit with additional features of rectifier and rotating current reverser. One more point to remember: for localizing the faults in underground cables, it may be ground faults or it may be short circuit faults, we can use Warley loop test and Murray loop test and Warley loop test. That is for localizing of faults. For localizing ground and short circuit faults. In underground cables. We can use Murray loop test. One is Murray loop test. Another one is Warley loop test is used. But point to remember, in these two loop tests, in Murray loop test and Warley loop test, in these two loop tests, during conducting experiment, a Wheatstone bridge is used. Clear? Then in Murray loop test and Warley loop test, the special feature of Warley loop test is it is more experimentally. In this Warley loop test, whatever we are locating the ground or short circuit faults in underground cables, this is more experimentally conducted. Warley loop test is more experimentally conducted as compared to Murray loop test. Okay, that is one advantage of Warley loop test. And one more point to remember: in localizing the faults using Murray loop test and Warley loop test, okay, the test resistance will affect the sensitivity of galvanometer. Whatever the test resistance we are using, that affects the sensitivity of the galvanometer. Okay, these points you remember with respect to measurement of resistance by using different methods. Okay, that points you concentrate. These special points I am giving.